Hello and welcome. In this video, we're going to be looking at a rule or a set of rules called the Hardy-Weinberg Principle that we use in population genetics. This is something that we do if we're looking at a group of people and we know that these people inside have alleles, pairs of alleles that determine their traits for a whole variety of things. It can include their sex, their physical structure, their vulnerability to certain diseases. And if we can track those on a population level, it means we can see if a certain trait is becoming more common or if a certain trait is fading away or if new people moving in are bringing in new traits that we haven't seen before. And all of that can be interesting, and sometimes we can help affect that through our understanding of genetics. So we're going to be doing a little bit of number crunching and counting involving alleles and people, and we'll use that to solve some interesting problems about populations and what kinds of genes they have. So when we get into this, one of the major things to know is that there's two levels on which we can count the genetics of a group. We can look at the level of people, or individuals, because you can do this with animals or plants, or you can do this at the level of alleles. If you're looking at this at the level of people, you're looking at genotypes. And so if you look at these three stick people, at the genotype level, you'd say, I have one person here who is homozygous dominant. 1 out of 3 homozygous dominant. I have 1 out of 3 who is heterozygous. 1/3 heterozygous. And I have 1/3 who's homozygous recessive. Okay, so we're viewing these as a pair like we normally do with a person and saying, here's the kind of trait that this person would exhibit. The other level we can look at this at is to ignore the people completely and just count the letters. Pretend that the people have vanished and all we have left are their chromosomes, and they're floating in a cup or something so that we don't know which one belonged to which person. We could still go through in terms of alleles and say I have 1, 2, 3 dominant alleles, 3 out of 6 dominant alleles, and recessive 1, 2, 3 of those also. It's a coincidence that those match, but because I made a simple example, but it's important to keep these two levels separate. Build a wall in your brain that has the pairs or the genotypes on one side and just the alleles on the other. There's one formula that governs how the genotypes work, and there's a different formula for the alleles, and a very common mistake is to take a number from one and plug it into the wrong formula. So if you're counting 2 at a time, you're working on the genotype level or the diploid level, or if you're a math person, the degree 2 level. And if you're just counting 1 at a time, then you're working on the allele level or the gamete level, or in math we'd call it first degree. And we don't want to get those blurred. Okay, so how do we use this? The big and famous Hardy-Weinberg formula is p squared plus 2pq plus q squared equals 1. And the less famous Hardy-Weinberg formula, still very important, is p plus q equals 1. This one, which in math we'd call second degree because this one has 2 p's, this one has p and q, this one has 2 q's. This one is looking at genotypes. This one is used for counting the people or the individuals in population and what genotypes they have. And the p plus q equals 1 applies to just alleles. Not whole people, just alleles or chromosomes. So if you're working with this formula, the p squared term represents people who are double dominant. Sorry, let me back that up very slightly. Hardy and Weinberg use p to represent dominant, and then they chose the letter q to represent recessive. So when they write p squared, they mean people who have the dominant allele twice. In other words, these people who have two dominant alleles. This term in the equation represents people with the homozygous dominant genotype. The PQ term represents people who are heterozygous. They have a dominant allele and a recessive allele, one of each. And Q squared represents people who have the recessive allele twice. In other words, people like this. They have the recessive allele twice. Okay, so this ties in with stuff we've already seen about the different genotypes that people can have. If you're wondering where this 2 came from, I don't want to get deeply into it now, but this comes from the 1 to 2 to 1 ratio that we saw when we were doing Punnett squares. This comes from the fact that there's 2 ways you can be heterozygous. You can get the dominant from dad, recessive from mom, or you can get dominant from mom, recessive from dad. That makes this twice as likely, and the formula reflects that. But what I want you to get now is that this formula is for when you're counting individuals with 2 alleles, and this tells you each term is for a different combination of alleles. Dominant twice, dominant and recessive, recessive twice. The other formula looks just at the letters and says P is the number of dominant alleles, so you don't care which people they came from, you're just counting alleles, and Q is the recessive alleles. And the equals ones tell you that each of these should add up to 1, as in the whole population, or 100%. And in this case, in my simple example, you can see 1/3 plus 1/3 plus 1/3 adds up to 1. And when we count the alleles, 3 out of 6 plus 3 out of 6 would be 1/2 plus 1/2. That adds up to 1 also. This is a pretty lame, simple example, but I've got a couple other ones set up on the next couple pages, which we'll do right away. So you'll get to see how this works, and I hope you'll find that it's not too bad. So let's do some counting. Here's a population, and I've made this first one a little boring just to get us warmed up, and there's a better one on the next page. What do you see here? We've got 10 stick people, and also we have 20 A's, right? Because each person has 2 chromosomes. And I say that to remind you that there's 2 levels on which we can count this. There's one level where we're going to look at people, and we're going to see how many of them are homozygous dominant, how many are heterozygous, and how many are homozygous recessive. And that should add up to 1 or to 100%. We can also count on the level of just alleles, dominant and recessive alleles, and those should also add up to 100%. So this won't take long because I've made it a very uniform population, but it'll show you how some of the numbers work, and then we'll get into something more complex. If you're counting here, P squared means count all the people who are homozygous dominant. That one, and that one is 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of heterozygous people is 10 out of 10. PQ represents the people who are heterozygous, who have big A, little a, and there aren't any of those. 0 out of 10. Q squared represents the people who are homozygous recessive, meaning little a, and there aren't any of those either. So 0 out of 10. And if you add that up, you get 10 out of 10, which is indeed 1, so apparently the formula works. Now, if we're counting at the level of alleles, that means forget about the people, just look at letters. Pretend that we took all these A's and threw them in a bowl, and now we're just counting through them. Number of dominant alleles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Number of dominant alleles is 20 out of 20. The number of recessive alleles, meaning little a's, there aren't any. 0 out of 20. That adds up to a total of 20 out of 20, which again comes out to 1. Okay, so this is a trivial case, but it shows that the formula works, and I hope it's getting you used to looking at the two different levels, looking at people who have two alleles at a time, or ignoring the people and just looking at their alleles and getting a total out of that. There's a formula for each one, and they are separate, and we'll see that again right now. Here's a population with some nice variety to it. You can see there's some big A, there's some little a, and there are plenty of big A, little a's. Let's see if the formula holds up here. I'll just put them up again. See, the formulae hold up here. P squared plus 2pq plus q squared equals 1. And the other level is counting alleles one at a time. P plus q equals 1. Okay. So, if we're counting p squared, do you remember what this is? This is people who are homozygous dominant. They have the dominant allele twice. So, for those we have this, and that, and this little person. That should be it. So there are 3 out of 12. I'm just quickly counting to make sure there are indeed 12 people. Yeah, so 3 out of 12 is the proportion of people who are homozygous dominant. Then for the PQ, that means heterozygous people, people who have a dominant and a recessive. How many of those have we got? Let's do a color switch here. That one's heterozygous, and there's 2, and there's 3, and that's 4, and 5, and 6. The 2PQ is 6 out of 12. You don't have to do anything with the 2 yet. For now, we're just know that the 2PQ, all of that is represented by the 6 out of 12. So don't worry about about doubling it or anything. The 2 has already happened. And finally, Q squared represents individuals who are homozygous recessive, meaning little a. We have 1 there, and 1 there, and 1 there, and yellow was a mistake. Sorry, I'll switch that. 1 there, 1 there, 1 there. Okay, so there's 3 out of 12 for them also. If you add that up, 3/12 plus 6/12 is 9/12 plus another 3 is 12/12. And that has to add up to 1. Okay, so that worked out okay. The other level we can look at down here is the allele level. In this case, forget about the humans. We're just looking at the chromosomes they have now, and we're counting how many are dominant, how many are recessive. So for dominant alleles, meaning capital A's, we have 1, 2, 3, 4, none there, 5, 6, 7, 8, 9, none there, 10, 11, 12. 12 out of, let's see, there's 12 humans, so there's 24 chromosomes. Okay, so there's 12 of the 24 chromosomes in this population are dominant. Now we're looking for recessives, meaning just little a's. 1, still 1, there's none there. 2, 3, 4, 5, she doesn't have any. 6, 7, 8, 9, 10, 11, 12. 12, 24, that adds up to 24 out of 24. Cool, it worked. Okay, so that's the level that we're working at, or those are the 2 levels that we can be working at, rather, counting individuals or counting just their chromosomes. And we're going to get into some practice problems in other videos, but I'm just going to show you very quickly what this could look like when we ask you questions about it. What's going to happen is we won't give you all this information. We'll give you a couple pieces and ask you to deduce the rest. So just decluttering this a little bit. Okay, so what if we didn't have all the big A's and little a's? Because in most populations we don't. We don't have genetic testing available for everybody. Let's say the recessive people in this group, little a, have something I'm going to call green feet syndrome. It's a condition that affects stick people, and it causes their feet to look green. So everybody who was little a here, suddenly we don't know all that. We don't have genetic testing on them, but we know that people with green feet are double recessive. Can we figure out any of the other stuff? How much can we tell from just the fact that we counted this population and we know that this many of them have green feet? Let's get our formulae up and we'll see how far we can get with this. Now I'm going to be solving this equation and doing some math that we have not gone into in depth yet. This is the first time we've ever seen it, and I know that, so if you don't have a perfect grip on this after the first example, it's okay, there's plenty more coming, but I'm just going to sketch it out in case you're curious what work with this is going to look like. So for this trait, here's some things that we know. We know that the big A trait produces a stick person with normal feet that look like a black stick like this. And big A little a also produces normal feet. But a stick person with little a has the recessive trait of green feet. And so looking at this population, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have a total of 12 people, and we found that this person has green feet, so does this one, and so does this one. So 3 of our 12 people have green feet. And of these other people, normal feet are a bit of a problem because we don't know if that makes you big A or big A little a. Either way, you'd have normal looking feet, but some of these people are carriers for the green foot trait, and we don't know which ones, but we're kind of curious how often that happens. So let's see what we can figure out from here. Now, up to this point, I've been treating these formulae like they're totally separate and these levels like they're totally separate, and there's no connection between them. But there is a connection, and it's that this Q is the same as this Q. And this P is the same as this P, which means we can use math to jump from one to the other. If you know that Q squared is 3 out of 12, here comes the math. If we know that Q squared is 3 out of 12, first, 3 divided by 12 is 0.25, so let's get that into decimal form because people are often happier this way than they are with fractions. Can we find what Q is from here? We want to know just Q, not Q squared, which means we want to unsquare this. And the way you unsquare a number is you square root it. We can square root both sides of this equation. You have to do it to the left and the right sides. And when you do, the square root of Q squared is just Q. In other words, the square root kind of strips the square off. And if you do the square root of 0.25, you find that Q is 0.5. So we had a number from the individual level, and now we've used that to find a number from the allele level. Q is 0.5 down here. What that's telling us is half of the letters in these that are hiding in these people must be little a's. And based on this, if P plus Q has to add up to 1, what plus 0.5 adds up to 1? P must be 0.5 also. So apparently half of the alleles, just the letters in these people, are dominant and the other half are recessive. Now, if you remember from the previous page, when we were counting these, we found that yes, they were an exact split. We had 12 dominant and 12 recessive alleles, and so the formula is telling us the truth here. Now that we know P and Q from the allele level, we can take those back up to the individual level too. If we know P and Q, we can say, hey, big formula, if I know what P is, P squared is 0.5 squared which is 0.25. This is the number of dominant, homozygous dominant people in the group. Apparently they must be 25%. This is saying 1/4 of our group is going to be homozygous dominant. And if you want the recessives should be 2 times P times Q. 2 times 0.5 is 1, 1 times 0.5 is 0.5. So this term tells us half of our group should be heterozygous. So just from knowing the number of people who are recessive, we can get everything now. We know that 1/4 of our population should be homozygous dominant, big A, big A. Half of them should be big A, little a, and we already knew that 1/4 of them, 3 out of 12, were little a, little a. We don't know exactly which ones, but knowing these numbers is helpful, and if we can watch if these numbers change over time, that's interesting, and we can tell how many people, for example, are carriers for the green foot trait. In case people wanted to know or wanted to do something about it, we could tell them how common these traits are. So, more practice on that coming up. We'll see you there.